So we have seen the working of the IC that is used, the DAC 7821 IC, okay, and we have seen how general DAC circuits work, what is digital domain, what is analog domain, what is a conversion from a practical point of view to do the experiment. So the IC that we are using is DAC 7821 as I just told, which is in the board. So again I am repeating, this board we are just using as an EC platform to convey our message of analog circuit design to you. It is not necessary that you need to use the board, you can always use these ICs or any other ICs from any other manufacturers to implement the similar functionality that we are trying to introduce to you. It is because of this reason, like you should be able to equipped to design any type of circuit using similar ICs made by different manufacturers. For that only we had introduced you to the importance of going through data sheet in the correct manner, and what should be the exact methodology followed, how quickly to go through the data sheet instead of spending hours together in going through the data sheet, how quickly to see the data sheet and arrive at a circuit design implementations. So that was the idea with which we have covered these topics. Now we have come to something what we can call the grand finale. Now we will see the exact circuit what we are going to implement, and then actually see it on the board after connecting it, and see how digital to analog conversion takes place and how it is differing from the theoretical calculations that we make. Okay. So let us see how we can design the circuit. Our intention also in this course is to make you intuitively design circuits. Okay. So just I will show you right now how you can intuitively design circuits. Okay. Let us say, so we are taking the DAC. So how will the DAC be? So after seeing the data sheet I showed you what are the important signals that you need to look at, right. So let us just show the DAC like this. Okay, the DAC is shown. So what are the main things? First is ground. Anyway, for any IC you will have ground, so ground will be there, clear. Then what else? Supply will be there, so VDD. Then because it is a digital to analog converter, it will have a reference voltage also, it is called Vref. Okay. Then what is it? Input, anything. So these ICs except for oscillators which are self generatory, with only power supply they can generate oscillating outputs. Most of the other ICs would need an input. Here because it is a DAC, correct. Here because it is a DAC we need the input. What is the input? Our input is a 12-bit parallel input, digital input, correct, because it is digital to analog converter. So that is D11 to D down to D0. Okay. Now what else is required? We know what is the output. So output in this IC as we have discussed before is in the form of current. So we have I out 1 and I out 2, correct. So what else is there? Yes, you guessed correctly. So there is one more main signal, that is for the R feedback, RFB. Okay. So we have made the DAC. So now we know that if we give sufficient supply voltages, if we ground it here, give reference voltage let us say 5 volt, give supply voltage because this IC works in 5 volt. So let us say we give supply voltage as 5 volt, and then we give input, we would get some output provided we have given sufficient feedback. So what is this feedback resistor? So you have already covered digital to analog conversion in the theory portion. So you might have gone through, I will not go into the details of it because this is a practical session. So you might have gone through the R to R ladder like this. So R to R ladder would be there, correct, and at the end of it the signals would be amplified using an amplifier, right, and there would be a feedback resistor like this. That is how the design is. So this resistor is this resistor, this feedback resistor. Okay. So but the resistor is already inbuilt because it is related to the resistor R to R network. The resistor is already inbuilt in the DAC. So you need to only give it to the op amps output, correct. Now so most of the outputs we visualize in all circuit design, we visualize as voltages, correct, and this IC is giving us output in the form of current. So next what we should do logically, so next logically what you should do, you have current and you need to convert it into voltage, correct, and the best IC or a component that you can use to do a current to voltage conversion is, as you must have learned during the duration of this course and you might learn during this course, is to use an op amp, correct. So, this much portion is your digital to analog conversion, correct. Now, we have the current to voltage conversion, correct. So, what to do to do that, what do you need? So, you need to connect first you put a op amp. So, in the board we have this TL082 op amp. So, we will use that, okay. The op amp will have output V out, it will have supply rails plus VCC and minus VCC. So, on the board ideally this op amp should work at from plus 10 ground and minus 10 volt, but we will work it out with plus 15 ground and minus 15 volt, okay, and it will work in these voltage rails also. So, it is designed for sufficient tolerances, okay. Then what do we have? Then we have the non inverting terminal and the inverting terminal. So, we will do the current to voltage conversion through the inverting configuration, okay. So, if it is an inverting configuration, what will be the non inverting terminal? The non inverting terminal will be grounded like this, okay. And then as we have discussed previously, the IO2 should also be grounded as per the guidelines given in the data sheet. So, the data sheet occasionally for every IC they will give certain guidelines, you should follow it, okay. Then the I out one is our current output, right, I out, correct, and we need to convert it into the voltage output V out. So, what do you do, and what is the input of the op amp for doing the current to voltage conversion? It is this inverting terminal. So, just convert this I out one here, okay. Now, next what it is? Yes, correct. So, feedback has to be, so now if you just leave it like this, it will still do current to voltage conversion, but what is the problem? There is, since there is no feedback given on this op amp, okay, since there is no feedback given for this op amp, it will work in what you call open loop configuration, okay. It will work in open loop configuration, but in open loop configuration it works like a comparator, and when it works like a comparator it will immediately go into plus V saturation or minus V saturation, which is roughly around 13.6 plus or minus 13.6 volt, which is roughly around plus or minus 13.6 volt, for a VCC of 15 plus or minus 15 volt, okay. So, we should have a negative feedback so that our gain is controllable and we will get measurable output values that change with the change in the bit sequence, because if we do not do that, right, in this circuit, whatever small input we give, because of the infinite gain of an open loop configuration of an op amp, okay, we will always get saturation voltage only as the output. That is why feedback is provided, and these are basic concepts in op amp which we will reiterate again and again, so that it becomes very solid to you, and you can use these concepts to build intelligent systems. Going further, we will see other applications also where we can build systems like such as these, okay. So, now our feedback is there, correct. So, our feedback now has to go to the output like this, correct. Technically this is all there is there for the circuit design to test it out, but then because of reference voltage fluctuations, supply voltage fluctuations or output current fluctuations, you observe something in practical circuit design called gain peaking, okay. What it is called? Gain peaking. What happens is, occasionally for a fluctuation in input voltages or output current here, okay, here we might get saturation output voltage as blips in the output. Let us say the output is supposed to be like this, and sometimes because of some blips we will get like this, okay, and this will be Vsat, saturation voltage, but we do not want that, this is not good circuit design. So, usually what is the component that you use to smoothen out your signals? So, yes, you guessed it correctly, the component used to smoothen out signals is the capacitor, okay. So, what we do is we will connect a small capacitor like around 0.1 picofarad or in picofarad or nanofarad range here across the feedback path and the input path, so that whatever peakings are there, it gets absorbed or smoothened out by the capacitor. Okay. So, this is how with this capacitor we will get smooth output signals, but we pay a price for this. I will not get into details again, but if you do circuit analysis of the output voltage, because of this capacitor you will find that the output gain gets reduced a bit, and we might not get the full voltage fluctuations at the output, but nonetheless we will be able to see changes output voltage as and when bit sequences are changed, which is digital to analog conversion, correct. So, let us go back. So, suppose we have V reference voltage of, let us say we have reference voltage of, let us say 5 volt, and you all know that this is a 12 bit DAC, correct. 12 bit DAC means it will have how many levels? It will have 2 raised to 12 equal to how much? 4096 levels, correct. And your total voltage swing is what? If say your reference voltage is 0 to 5 volt, your voltage swing will be 5 volt, correct. So, your step size voltage, step size voltage for each change in bit sequence would be 5 by 4096. You can do mind calculation itself on this, you did not use calculator for this. This will come to around 1.2 millivolt for each change in bit, correct. But then there is one more thing, because we are using an amplifier stage and it is a negative feedback amplifier, and we do not actually have a feedback resistor, we have capacitor only in the path. So, the amplitude, the maximum amplitude may get reduced when we actually practically implement it. That has to do with all frequency changes, noise levels, everything in the circuit. So, we will see what is the base level when we start off with the bit sequence of say 0 0 0 0 0 0 0 0 1 first bit turned high, then we will turn this to 0 and turn this to 1. So, that 1 bit change we are making, we will see what is the base voltage we get and what is the increment per bit. So, ideally we should get around 1.2 millivolt, we will see how much we get, and we will also see what is the maximum voltage we are seeing, okay, when we see the circuit. Clear? So, this is the circuit that we are going to see now. This we will connect it up in the board and see how digital to analog conversion happens. Okay. Now, let us see the board. So, this is the board. As we have explained in previous lectures, this board has 2 DAC systems, okay, same IC, 2 sets of circuits, same circuits are provided on the board. So, we are using the top section, okay, we are using the top section, and what are the main, we have already seen the circuit design. So, we will just go through what are the main things should look at here, and then see the connection and see what is the output we are getting, okay. So, this is the tri-state switch that is provided for giving the bit sequence. So, from D11 to D0, okay, 12 bit tri-state switch, okay. So, here we can have 0, 1 or a tri-state level to give 1, 0 whatever bit sequence we need, okay. And then we have the supply lines, and there is something called digital logic supply here, which is the logic line supply voltages. So, this we can give through either the DC voltage or through the low dropout voltage. So, this is DC and you can have a switch selection. So, we have kept the DC level, okay. And then so same the main 3 connections that so you might have, there are 5 main connections here. After that, one is actually 6 main connections. We have gone through the chip select line, right. So, this is the chip select line. So, it has to be 0 for this chip to be selected. So, it is by default grounded routed to 0, and if you want to bypass it, you can bypass it also through this burg. And we have the read or write burg, that is this. Same connections are there in the top section also, because this is more visible to you, we are explaining with this, plus the connections are also not made on this block. So, it is more easy for you to visualize, okay. And then what is there is the reference voltage. What is the V reference voltage for your digital to analog conversion? So, that is given through this burg, okay. We will be giving 5 volt V reference voltage from the same DC converter which we are using to give supply to the digital logic supply here. Same supply we will be giving to the reference voltage, which is here, if you can see, okay. Then the other 3 main lines are the output and the feedback resistor. So, this is I out 2, this line is I out 2, this line is I out 1, and this line is the R feedback. What is the importance of R feedback, what is the importance of I out 1, what is the importance of I out 2, everything we have covered just now when we did the circuit design. Okay. Now, let us see how the circuits are connected by zooming out. Okay. Cool. So, the I out, as we have seen, we have to connect the output and the feedback to a op amp section here in an inverting configuration. So, the I out 2 is connected to the ground here, and also the non inverting terminal here plus is also connected to ground here, and I out 1 is connected to the inverting terminal input here, you can see it, and then the feedback path, that is here, is connected to the output section here as per our circuit design. Okay. And we have also connected, so as per the circuit design here it is there, we have connected it, and as per our circuit design we have also connected a capacitor between the feedback line which is there in the. So, if you have to add an extra component, we have to use the breadboard that is provided, we have seen that. So, we have used a capacitor above here, if you see. So, we have added this capacitor, this yellow color component which is a capacitor. Okay. This capacitor we have connected between the feedback line and the inverting input terminal as per the circuit design for avoiding gain peak. Okay. Now, we are all set to see the connections. Now, let us focus on the tri-state logic for the bit sequence. Okay. Now, you can see it. So, if you see now, what we will do is, we have given supply, everything is done ready, as I have told you that because of the circuit limitations and because of the fact that we have added a capacitor for gain peak adjustments, we might not get the full output swing, but still we will be able to see what is the change in output voltage when we change the bit sequence, which is what digital to analog conversion is. So, now if you see the bit sequence, the bottom position is 0 and the top position is 1. Okay. So, now we have given 0 0 0 0 0 0 with last bit as 1. Let us see what is the output voltage. So, we have a multimeter. So, we have a multimeter connected to the output line and ground to see the output voltage. Because we have used the inverting configuration, we will get negative voltage as the output. Let us now focus on the multimeter. Yes, now you can clearly see it, correct. So, what we are saying, so our bit sequence is 0 0 0 0 0 0 last bit 1. So, we have got 28.5 millivolt, okay, correct, around 28.5 millivolt. Now, as per our calculation, we did that 5 by 4096, roughly for every bit change we should get around 1.5 millivolt increase. So, let us see what we are getting now. We will make the second bit 1 and make the first bit 0, so that we are doing only 1 bit change. So, now what we have done, is now we are probing it again. So, it was 26.4 before, now we are getting 28.8. So, it is around 2.4 voltage, roughly we have got around 1.5. So, we are getting in that range the voltage change. So, you remember that this is in millivolt range. So, noise components also will be there, but we are seeing a change. Okay. So, now now what we have done, the D1 bit as high and brought the D0 bit as 0. Now, I have keeping the multimeter as it is connected with my this hand. Let me just change the first 0 bit also. Now, 2 bits will go high. So, accordingly you see a change in voltage, it has become 31.9. So, it is roughly 32 millivolt. So, what was the previous voltage? It was 26.4. Now, we added 2 bit change. So, we got a change of around 26.4 to 32, correct. So we got around 5.86 around 6 millivolt change. Now let's increase one more bit. Now we are keeping the other two bits high, so we are going in not in changing one bit at a time, we are changing actually double, because we are not going removing the other two bits to 0, we are keeping them as 1 and keep on increasing the increasing bits to high, that is D0 D1 are 1 now. Instead of keeping D0 D1 as 0 and then changing D2 to 1, we will do D0 high, D1 high, D2 high. So instead of getting 1.5 to 2 millivolt increase per bit change, we will get double of that, around 4.5 to 5. Here we are getting around 5.5 millivolt, but roughly in that range we will get. So now D0 is high, D1 is high, and we are getting around 32 millivolt change. Now I will make D2 as high. To ensure that our circuit design and connections are proper, the best way is to make sure that we are able to predict what voltage we will get when we make a change in the circuit. That shows the robustness of our design. The calculated values might not match, but the curve, the relationship or the linearity, if at all the relationship is linear, should be maintained. That is what we should look at. So now we saw that by retaining the other two bits as high, by adding one more bit as high, we will get around 5 to 6 millivolt increase, correct. So this should go to around 37 to 38 millivolt when I change D2 to high. So let us see that. So we will change D2 to high. Okay. So now we have changed another bit now, which is the D2 bit, correct. So we are getting 77.7, roughly 77 millivolt. Why are we getting like this? Yes, you have to you have to understand that each bit has its own weight. So 0th bit is 2 raised to 0, first bit is 2 raised to 1, okay, and the D2 bit is 2 raised to 2, that is 4. So your relationship is not actually linear, but you are having a not exponential, the a raised to 2 or the 2 raised to a curve, if you actually look at the mathematics of it. Because of that we are seeing this change. So we jumped from around 37, because now it is what earlier what it was 2 raised to 0, 2 raised to 1, now it is 2 raised to 2, it is almost doubling from 2 to 4 the weight of that bit. Because of that we were having 37 millivolt, we came to roughly around 78 millivolt range. Now let us change the next bit and see what we are getting. See this. So we got 136, 137, it is doubling, because we are changing we are adding one weight per bit. Now from 2 raised to 2 bit we have gone to 2 raised to 3 bit. So we are adding one more 2. So it has become 137 millivolt, but you can very clearly see the digital to analog conversion happening. From a low voltage of 31 millivolt, 26 millivolt with 1 bit high, we have reached to 137 millivolt. To make sure that this is working properly, let us go back to our ground state. So I will make these D3, D2, D1 bits 0 and then retain D0 bit as high. So we should go back to something around 26 millivolt. Yes, we have gone back to 26.2 millivolt. That means that the circuit is working very robustly. Now what I will do is, we will make the last bit D12 bit high, which has very high weightage. So because of that the voltage will go to a reasonably very high value. Okay. So I have changed the bit sequence. So we are getting 236 millivolt. Okay. 244 if I change one more bit. Let us change one more bit now. 249. So this is how the digital to analog conversion circuit works. So I hope you understood how the voltages are changing when we change the bit sequences. We can even use this digital to analog conversion circuit, and we have understood why current to voltage conversion is required, so that we can see the voltage itself and make use of the voltage for other further applications. So this completes the digital to analog conversion experimental part, and we will also see if we can use this module for other interesting applications. We will be seeing another interesting application of analog circuit design, where we will see how the analog circuit design can be done at the interface of digital and analog domains. which is quite interesting from a mixed signal design point of view. This is not exactly mixed signal design, that is an entirely other beast in itself, but you can get a few flavors of mixed signal design where your PCB will handle both analog and digital signals. That is the essence of mixed signal design. So today what we will be seeing is digitally controlled gain stage amplifier. We won't get into much theory about it, but like we have seen in our DAC module, we will see how we can intuitively design digitally controlled gain stage amplifiers. Intuitive design is what we want you to develop in the course of during the duration of this course. Because this is a more practical oriented course, at the end of it we expect that you are able to design a few basic systems on your own from the top of your mind without actually looking up the internet for circuits, which is what many of us do. So let us see. So what we are trying to do is digitally controlled gain stage amplifier. Let me give you the intuitive way of designing this circuit. So what is the amplifier? Okay, let us say you all have covered, you must all have become now experts in non-inverting amplifier configurations, correct? So let us see how non-inverting amplifiers are designed. Non-inverting amplifier, how it will be? We will have an op amp. So you have plus minus output, you give the input directly to this V in, and you will have a feedback, negative feedback resistor R2, and you have another resistor connected to ground, which is R1, and your output will be V out is equal to 1 plus R2 by R1 into V in, correct. So these things you already know, these are the basics of an amplifier, inverting and a non-inverting amplifier. So this is a non-inverting amplifier. Same way the inverting amplifier, how does it look like? Quickly let us go through it. How does the inverting amplifier look like? The inverting amplifier looks like this. So you have the op amp again, you have the output, you have the inverting terminal, you have the non-inverting terminal. The non-inverting terminal is grounded. You should always make sure that for amplifiers you should have negative feedback, okay. And then we have V in here coming here, and you have another resistor, you have RF feedback resistor, you have R1, and your output is what? V out is equal to minus RF by R1. So this is your inverting amplifier configuration, correct. Now what we are trying to do here today is not exactly related to any of this. Will it be possible for us to on the fly using digital logic change the gain of an amplifier? So that is what is meant by digitally controlled gain stage amplifier, okay. That is what is meant by digitally controlled gain stage amplifier. So how can we do that? So that we will do by integrating a DAC to the amplifier stage. So already we have seen an experiment where we have given a bit sequence to the DAC, correct. We have given a bit sequence to the DAC and it has gone, it will give a current output, correct, and the current output is converted to a voltage, correct, and the voltage we will visualize as the analog version of the digital input signal. So can this voltage be used, correct, can this voltage be used to give, what is it, a differential or a controlled gain to an amplifier. Remember that this DAC, so remember the DAC output when we saw it was a negative voltage, correct, and we have covered now that, what is it, we have covered now that when we are designing amplifiers the feedback should be negative. So for the feedback to be negative, either your output should be connected to your inverting terminal, correct, or you can connect it to your non-inverting terminal, but your feedback voltage itself can be negative. In two ways you can have negative feedback, correct. You can either convert a positive, you can either connect a positive voltage, a fraction of the positive voltage of your output to your negative terminal, correct, this is negative terminal, correct. Or how you can do negative feedback, you can convert a negative portion of your output voltage to your positive terminal, that is also negative feedback, correct. These are two ways you can do it. I am trying to tell you how intuitive design is done, that is why we are going like building blocks here, correct. So which scheme do you choose? Anyway we need to control the gain of our amplifier, correct, and we are telling that we are going to control it digitally, we are using digital control, we are using digital control for the gain of your amplifier, correct. So and we also know that our DAC output as per our previous experiments is a negative voltage. So output is negative, we will use a fraction of that output voltage to give feedback. So if we use this scheme, here also it will be negative, here also it will go to the negative terminal, so you will get overall positive feedback and the output will saturate or oscillate, okay. So instead of that, this is not the scheme that we should choose. Is it understood? Hope it is clear to you. So we have to use this scheme, correct, we have to use this scheme for giving negative feedback, and negative feedback is what is required for amplifiers, and negative feedback is required for amplifiers, and positive feedback is used for, yes correct, oscillators, correct. So one learning is done. So what we are doing, we are taking a problem. What is our problem? Our problem is to design a circuit to do digitally controlled gain stage amplification. Our problem is to do digitally controlled gain stage amplification. So we are breaking down the problem and seeing how digital control can be incorporated into gain stage amplification. For that we know the amplifier design, which we have covered, which is very simple. So amplifier design is very clear to us, okay. Now amplifier design is very clear to us, and we know that in amplifier we should have negative feedback, but we have the constraint that in our digital control our DAC output is negative. So how can we implement negative feedback using an output which is already negative? What we have to do? We have to use this scheme. Is it clear to you? This is how we do intuitively design. So it is very clear, things are coming automatically to you, okay. So let us get into the get our hands dirty and get into the circuit design, correct. So now we know that our feedback should go to the negative terminal, correct, positive terminal, because our output voltage itself is negative. So let us make the circuit. So our scheme will reverse, so this will be plus and this will be minus, and this will be our output voltage, okay, V out, this much we know, correct, because scheme is like that. We will ground this terminal, clear. Now we will give input here, V in, through a resistor R1, okay. So we have another resistor here, R2, clear. Now if we connect R2 here like this will become positive feedback, because your output is already positive, because it is a non-inverting configuration, correct, and you are giving a positive feedback. So this will go into saturation and even oscillate, correct. So then this is not what we should do. Here is where, so here there should be something that can do two things. What all? One is give a negative output, negative voltage contribution. Another is controlled output voltage using digital bit sequences. Correct? Two things. It should have negative voltage so that we will have negative feedback, so that amplifier operation can work properly, and we should have controlled output voltage that will change with bit sequences, so that we can do a digital control of the gain stage, which is, this is the gain stage, this is the gain stage. So the gain stage of the amplifier can be digitally controlled using a DAC. This is where the learnings you take from your previous modules okay, you can use to make beautiful circuits. These circuits, if you look at it from a practical implementation point of view, these are beautiful. I will come to the practical implementation of it, how important this circuit is. That's why we wanted to cover this part with you. Okay, now this part is clear. Now you are all masters of this part. Now we have to make a DAC, right? So let's make that DAC separately here. Okay, so this will be the fixed amplifier section. And this is the DAC section for us to digitally control our amplifier, correct. So let's not worry right now about connecting these two and getting our final implementation, which is the digitally controlled gain stage amplifier. Let's see what DAC section we have to do. DAC section, now I think you all are very well aware and you are masters of that part. So let's just do the formality of designing it. Okay, so let's take a DAC. So we will have a VREF, let's keep it there. You have a VDD, you have a ground which is grounded here. Okay, you have a feedback resistor RFB. So this is your DAC. Okay, you have IOUT1, you have IOUT2, correct. Okay, as per our previous design, IOUT2 should be grounded, correct. And for us to do current to voltage conversion, this we have to connect to another amplifier. All this is, I think, very clear to you now. So the amplifier will again have a negative feedback. So the positive terminal will be grounded like this along with IOUT2, correct. And IOUT1 will go to the negative terminal like this. Clear? Clear, right? So what will happen? This is the output of the amplifier, which will be a negative voltage, correct. Now we know that the feedback has to be connected to the output. This also is very clear to you, we have gone through it in detail. So the feedback is connected. Now what is missing? What is missing from our previous modules? Yes, we need to do the control for gain peaking. So we add a capacitor here, correct. Cool. Now what we have done? So this DAC portion is ready, it is ready here, cool, that portion is ready. Now we have the fractional. So we what else is missing here? We missed a very important thing here, correct. We missed the digital input, no. So digital input will be there, D11 to D0, which will control the output that you finally get here, correct. So what is the control here? So you are able to control the voltage here, VO1, using the digital bit sequence here, correct. Now how do you connect these two? Now we understood, we have learned that this feedback path, for it to become variable and controllable, what is it? Variable and controllable. For it to become variable and controllable, there should be some negative voltage that we can control, that should add on to this voltage, correct. So it is obvious, correct. So that we should connect these two, correct. So this voltage that is coming from here, this part gets configured by this bit sequence and it gets added on to the feedback path. Now still the feedback part is not completed, correct. The Vout is still dangling here. The Vout should finally connect here, no. Ideally it was connecting here, but then we have added a changing negative voltage, controllable voltage component there. So it is simple now, you understood, right. So this has to go back as your reference voltage, so that we complete the circuit. So your output will go as your reference voltage. So the reference voltage will control the levels of your output voltage here, which will give a negative voltage, and that will add on to the feedback path here, and we have our input voltage, and we can see how we can control the gain with this mechanism. See how beautiful the circuit is. It's very beautiful, right. We have used two concepts which we have learned. What are the two concepts which we have learned? One is digital to analog conversion, and in that process of learning that we have learned current to voltage conversion, okay. And we have used, so we know that with a bit sequence applied at the input of the digital to analog converter, we can have a negative voltage that is concordant, corresponding to the input bit sequence, correct. And then we also studied about amplifiers, what is amplification, what is feedback, what is negative feedback, what is positive feedback, what is non-inverting amplifier, what is inverting amplifier. These two strong concepts which you have learnt, we have integrated to make something beautiful. What is the beauty here? Here you will be able to control the gain of your amplifier by using the bit sequence. Now you might think, what is so special about it? I have to still change the bit sequences, right? I have to still change the bit sequence. What is so digitally controllable in that? Yes, that is where you might be missing the point. The beauty I will show you now. Suppose we have a PCB, okay, and you have an analog section in the PCB, and you have a digital section, clear, and your digital section is controlled by, say, a microcontroller MUSI, okay. You have the analog domain which has lot of amplifiers, let us say, and other filters and all sorts of modules, oscillators, filters, everything, oscillators, filters, all these are analog domain. This is your analog domain, okay. This is your digital domain of the PCB, okay. Now if you do a hard coded design, your amplifications will be fixed. So during the time of bringing up of your PCB, this will kind of become your mixed signal PCB. During the duration of picking up a PCB, you will be faced with either to desoldering of the resistors that you have used for your amplification and finding out new resistors and then placing them back, soldering them back to change your amplification, or you can use this beautiful circuit to control the gain digitally. But what will happen? This amplifier, as we have seen, will get connected to a DAC module, correct, and the DAC module, what it will have? The DAC module will have a bit sequence, correct, and we know that by changing this bit sequence you will be able to change the amplitude of this output, the amplification, and there comes the beauty. You have connected the analog world, correct, with the digital world, because your microcontroller will be able to talk to these bit lines, and through your software which is loaded on the microcontroller, you will be able to change the bit sequence and thereby change the output voltage without touching any component on this PCB. Even after you deliver this as a product, suppose, and your customer faces some tuning issues, some calibration issues because of the amplifier's output, you can always give a software upgrade to your board, updating the firmware on your microcontroller, which will change the bit sequences and you will give the output. There is no soldering, desoldering involved. This is the beauty of such a design, and we wanted you to appreciate this beauty, okay. So this is how we can merge digital and analog domains, and this is how analog circuit and digital design goes hand in hand, okay. So now I guess you are very well aware of the importance of the circuit, how we have done this design intuitively, step by step, understanding each and every module in a very practical way. We have not got into the mathematical formulation or anything, we have just taken blocks, connected them together, and now comes the fun part. We will see the board and see if it is working. So here we have the board where we have implemented what we just saw as circuit. So what did we just see? So we had the DAC, and we are trying to integrate an op-amp based amplifier with digital to analog converter, so that we will be able to control its gain digitally. So that is what digitally controlled variable gain amplifier, that is what we are trying to see. So here, as we have seen before, this is the DAC setup, that is a digital to analog converter setup, and we have the IOUT 1, IOUT 2, R feedback, everything connected, okay. So in this implementation, as is seen by the circuit that we just designed, we have 2 op-amps to be used. So these 2 op-amps, so here you can see this is op-amp section. So we have one op-amp here and another op-amp here. So one op-amp, as we have seen, is used to convert the current output of the DAC to voltage, and that gets fed back into the feedback network, correct, and then is used up by the other op-amp, whose output goes back as the Vref for the DAC, correct. So these connections have been made here. Hope it's kind of lot of connections are there, because we are trying to use the jumpers on the board and connect up, but the basic idea remains the same. So the DAC, which is this one, okay, the DAC is connected and its bit sequences are here, okay, and then the output of it I out 1 I out 2 goes to ground, as well as the positive terminal of the op amp goes to ground, okay, and the I out 1 goes to the negative terminal of one op amp, and R feedback goes to the output of that op amp here, and then both of them are connected through a capacitor here above on this breadboard. If you can slightly go up, yeah, but you can see you had seen it in the DAC setup also. So, there is a breadboard here, this white color section. So, there we have kept a capacitor, this white section. Then from the output, okay, from the output of that op amp, we have a resistor connected. So, we have a two resistor network R1 R2. We have right now we have kept both same resistors. So, here we have connected the two resistors as we have seen. So, we have seen right the amplifier in which the input was connected to the positive terminal of the op amp through a resistor, and the feedback path had a resistor on it that was connected to the DAC, digital to analog converter system. So, these two are the same resistors. For simplicity purposes, we have kept the same resistor values here. Then that output, so this goes to the second op amp here below. So, let us see that, yes. So, it goes to the second op amp here below, okay. From here the output of this op amp goes back as the reference voltage for the DAC. So, this green wire which I have held up, you can see. So, this is the port for the voltage reference, and it gets connected to the output of the op amp. So, this way the circuit is completed, okay. Now, we can see the output. So, the output is the output of this second op amp, which also goes as voltage reference to the DAC system. So, let us see how by changing the bit sequence we are able to see the change in the output voltage. So, if you see the power supply, the input voltage is applied from this power supply. The plus 15 minus 15 supply for the op amps is given from this power supply, the central power supply. So, we are applying an input of 0.05 volt or 50 millivolt, okay, and that signal is applied to this, and through the resistor here. So, that signal is applied through the resistor here, okay. Then now we will see the output by looking at the output of the op amp. Now, let us just focus once at the bit sequences. Yes, now we can see the bit sequences. If you can see, now all the bits have been pushed up like this. Now, we will now only focus on the multimeter after this. Now, I will be you will not be seeing it, but I will be changing few bits in this, and we will accordingly see in the multimeter how the voltage is changing. Now, let us see what is the voltage when all the bits in the DAC are high. So, let us focus on the multimeter. So, I have not yet connected it. So, it is showing minus 309 millivolt, okay. For 50 volt input we got an output of minus 309 millivolt. Now, let us just change the bit sequence. So, I will change few bits to 0. So, you can see very clearly the voltage has gone up, it has become 411 volt or 411 millivolt, 0.41. It was a lower value before. Let us just go back to that lower value. So, that is 316, okay. It has almost gone up by 1.1 volt or 100 millivolt. So, gone up in the sense by absolute magnitude it has gone further negative. So, let us just change another bit combination and see how the output is changing. See, as and when I am changing the bits, the voltage is changing. It has become 0.6 volt. So, let me change more bits. So, it has become 0.745. I will check one more, change one more bit. it has become minus 0.966. See, so through this way we are able to control the gain. So the gain, so we are seeing a swing from like 300 millivolt to only around 0.9 millivolt, right? That's because our input voltage is very less, because input voltage is very less because the amplification will be there and you do not want the op amp to go to saturation, correct? See, I have changed a lot of bits now, so it has gone to up to minus 2 volt for 50 millivolt input. Now let us just do a small experiment. Let us just increase the input voltage to let us say 0.07 or 70 millivolt. So you just focus on the multimeter. I will just change the input voltage. So now it is I have increased it to 0.09 or 90 millivolt. See the voltage now, it is minus 1.333. So let me change the bit sequences. So it is coming down. See, so it is fluctuating. In the sense it is not fluctuating, it is changing as per our changes of the bit sequence. And one more thing to notice is that, so when I go beyond like 100 millivolt, because the gain op amp, we have two stages of op amps here, the input swing should be very minimal. It is used for processing very small input voltages. The moment I go to a high voltage, so till 290 millivolt it is okay. Whatever which gave 300 millivolt for 50 millivolt input, my input is now 0.290 millivolt. So accordingly our DC output has become 4.3 volt. Okay. Now it is 290 millivolt. Let me increase the input voltage. See, so it is 260 millivolt. Okay. Now if I increase it, at one point it suddenly goes to saturation. It has gone to positive saturation, because now the amplitude, the amplification has become too much that it has gone to positive saturation. So this way we will be able to digitally control the amplitude. Let me go back to the low 0.06, 0.05. So it is 0.08, 80 millivolt, okay, and this is the output voltage. Let me change the bit sequences. So you can see the voltage changing. Okay. So this is how digitally controlled variable gain amplifier can be made. As I have told, you need not actually go ahead and change these bits like I am doing it. This is only for educational purposes, we are showing it like this to you. You can always have a microcontroller connected to your DAC input bus and change the bits accordingly. So I hope this circuit was you found the circuit interesting, and in further modules we will see other circuits as well. Thank you.